Find the Maclaurin series for f of x equals x squared times e to the x. We can take the derivative of this function successively and build the Taylor series, or we observe that we have the series representation for e to the x. E to the x is a series x to the n over n factorial. And so x squared times e to the x is x squared times the series, which is x squared times 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. But we can bring the x squared inside the summation to have x squared times x to the n over n factorial, which is x to the n plus 2 over n factorial, starting with n equals 0. If we start with n equal 2, then we just simply shift the series to the left 2 units by replacing n with n minus 2. Notice that we can multiply x squared into the series to get x squared plus x cubed over 1 factorial plus x to the 4 over 2 factorial. And we observe that the exponents are now 2 more. And so that is why n plus 2. Another example, let I be the definite integral of sine of x squared dx from 0 to 1. We know that we cannot find the antiderivative of sine of x squared, but observe that sine of x is the infinite series, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So sine of x squared is the same series, but we replace x with x squared. And this is the series negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. And so sine of x squared is x squared minus x to the 6 over 3 factorial plus x to the 10 over 5 factorial minus x to the 14 over 7 factorial plus ... We then integrate both sides of the equation with respect to x. The antiderivative of x squared is x cubed over 3. The antiderivative of x to the 6 is x to the 7 over 7. The antiderivative of x to the 10 is x to the 11 over 11. And the factorials in the denominators are constant, so they are the same. The definite integral from 0 to 1 can be evaluated by using the fundamental theorem of calculus. The integral is f of 1 minus f of 0. But f of 1 is 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus, and so on, minus f of 0, but f of 0 is 0. And so we see that this is an alternating series where b sub n is approaching 0 and b sub n plus 1 is less than b sub n because the denominators are getting larger. And so this series converges. The error is using the partial sum of an alternating series s sub n is always less than the next term b sub n plus 1. And so the remainder r sub n is the absolute value of s, which is the actual sum, minus s sub n, which is the partial sum, is always less than or equal to the next term that we do not use in the partial sum. For example, the remainder using 2 terms is less than b sub 3. The remainder using 3 terms, s minus s sub 3, is less than b sub 4. b sub 4 is 1 over 15 times 7 factorial, which is 0.00001. But s sub 3 is 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial. And this is 0.31028.